Hi, yeah, how's it going? I want to have a look at triangles for ray tracing. And before I really look at triangles, I want to go over a concept called barycentric coordinates. So barycentric coordinates are a coordinate system which is commonly used in triangles. So imagine, let me start with a line. So imagine we have a line segment between 2 points, this point and this point, and we are interpolating between the two endpoints. We could use a sort of interpolation parameter. So we could say, at some point here, parameter equals 0, we're at the left point. At another point, parameter equals 1, we are at the right point. Fair enough. Another way we could interpolate is we could make a coordinate system, two component, where one means that we are on the left. Sorry, the first coordinate, 1, means that we're on the left point. The second coordinate, 1, means that we're on the right point. And if we are at any point in between, then we could, let's call this S, and then we'll go 1 minus S for the other coordinate. So we have a conservation that the two coordinate pairs always sum up to 1. Let's just say that. Now, the concept of barycentric coordinates are pretty similar. So we have three corners, and I'll say this first corner corresponds to a first coordinate being 1. The second corner corresponds to the second coordinate being 1, and the third corner corresponds in the coordinate system to having the third coordinate at 1. And then any point in between will be some linear combination of the three coordinates. And if all of those, well, okay, first of all, they all need to be, there's a term here, it's called a concave interpolation or something like that. And it's basically, we'll have a point inside the triangle so long as all the coordinates are bigger than or equal to 0, and their sum is less than 1. But let me just denote this P, and we'll have W as the first coordinate. Yeah, let's go U for the second coordinate, V times the third coordinate. So imagine we have 3 positions. We take those 3 coefficients. Remember, W, U, and V have to sum up to 1 and sum them together. And this lets us interpolate any arbitrary attribute of a triangle. So for instance, we could be storing the individual colors. I wonder if I can do this. Okay, let's go with that. So if we store the individual colors at each of the corners, well, then we can interpolate between them based on this coordinate system. Same thing goes with normals. So if we load in a model and we have a normal on a per corner basis, then we can interpolate those normals just the same way that our rasterizer does in the fragment shader. But anyway, so I think that was all I was going to say right now on barycentric coordinates, but we will be using barycentric coordinates for our tests. So let me set up another situation. Let's say we have some sort of triangle here, and I'll label the points. So I'll label this point A, B, and C. So we can work out some things. So if we run from A to B, that will give us one direction vector. Run from A to C, that will give us another direction vector. And then the cross product of those two, of course, will give us the normal. So I'll just put a normal vector here. And then imagine we have some ray coming from some origin with some direction, and it shoots down, and we want to know first of all, yeah, it'll hit the point like a plane, but then we want to know, is that in the triangle? So here's how the process works. If we were to look at this as if it were a plane, then of course we have the fact that the normal is the direction vector AC cross AB. And of course the normal direction does matter, but if we're going the wrong way, all we need to do is flip it around, because every surface has two normals. No worries, that's fine. For this one, I'm going to pretend that the triangles can be double-sided. Why not? Now, because we're on the plane, no, we can leave that. We can leave that. Here's the important bit. The important bit is that the point, if I put P here for point, the point of intersection is equal to W times the point A, U times the point B, and V times the point C. And I'll just put little tildes here to indicate that these are vec3s. Now, because we have the fact that W, U, and V is equal to 1, then we can rearrange this and reduce the number of variables in the system. So we can say, okay, swap that out. So we have 1 minus U minus V. Okay, that gives us the point. Now, as well as being a point, the point of intersection here is on the ray. So we have another fact. We have the fact that the position has to be equal to the ray's origin plus some parameter t times the ray's distance. So if we look at this, we can equate these two equations, and then there are three unknowns that we want to solve. We want to solve for t to see how far along the ray we've traveled. We want to solve for u and v to see the bounds of the point and see if it's within the appropriate bounds. So what we'll do is equate these two, and I want to keep all the, this will be messy, but let's write it. So let's multiply this in. So we'll have A minus U times A minus V times A. This will take a second. Okay, so that was from the triangle equation, from the plane stuff. And then on the other side, we have the position as it relates to the ray. Okay, now I'm going to put the knowns on the left-hand side and the unknowns on the right-hand side. So on the left-hand side, I'll have the point A minus origin. And on the right-hand side, let me group this together. So we'll have d times t plus, A minus b times u plus, A minus c times v. This is a lot of fun. So what we've got is, if you look at this really carefully, this is really closely, this is a linear combination of row vectors. So if we were to write this, we were to say point A minus the origin, that is a vector, that's a vec3. And then on the right hand side, we have, if we imagine taking that D as a column, and then take that A minus C as another column, and this, whoops, what am I writing here? A minus B, and this A minus C as a third column, and then multiplying that through by the column vector T, U, V. So if we were to, again, if we were to expand this out, it would be the would be the first column times the first row, second column times the second row, third column times the third row, just like that. Okay, so then the question is, whoops, what? Where was I? There we are. Okay, so the question is, we have a matrix system. This stuff is known. All of this is known. This is unknown. We can solve this by Cramer's rule. And Cramer's rule is a bit of a, well, I mean, there is logic behind it, but it's sort of peddled as a, if you don't want to solve linear equations the hard way with inverses, and this is like a neat little thing. And it only really works up to 4-dimensional systems, then it just becomes untenable. But what we do is we solve this by a quotient of determinants. So I have a determinant of a 3 by 3 on the top and bottom. On the bottom, it's always the original matrix. So with the columns D, A minus B, and A minus C. That's on the denominator. Now on the numerator, what we do is T is the first parameter here that we want to solve for. So we go back into this matrix and we swap out in the first row with the right-hand side. So we'll take that A minus origin, because that's the right-hand side, put it in the first column because we're solving for the first unknown, and then the rest will just be the original system matrix, and so on. So then as another example, if I wanted to solve for U, I'll do the same thing. Okay, so U is the second unknown, so the system matrix stays the same, except in the second column where we put in the right-hand side of the equation. And the denominator is just the original system equation. And so on. So hopefully that sort of makes sense. Let's jump into the code and put it into practice. So what I've done is I've got a scene. It's all set up for us. It's got triangles. I took care of the implementation of defining the triangle class and everything, because that stuff, it's not that exciting. It's just a whole lot of coding. No worries. But the triangles are there, they're randomized, and we need to develop a shader function to display them. Okay, so let's get into that. Okay, so like I said, the rest of this project has been set up for you. I would recommend going in there, having a little look, but otherwise it's pretty similar to everything we've done in the past. I'll just make a little note. So you may remember that I would always talk about how, what am I saying? I would also always talk about memory alignment when we're sending stuff to the GPU. We have this triangle. This triangle has 4 vec3s, 3 corners and 1 color. And 3 times 4 is 12. So it might be tempting to say, hey, we can just throw in 12 floats and that will be, do you know what I mean? Do you know what I mean? Anyway, but there is some implicit padding, an extra float's worth, of padding between each of these vec3s. And if you were to run this with just one triangle, you'd actually find that issue. It would complain and say, hey, you haven't allocated enough space for the buffer. But anyway, that's just something to bear in mind. Otherwise, it's all the same stuff. And what I want to work on right now is this hit triangle function. Whoops, 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 whoops. There we go. Accidentally had my worked solution up. So this is the one. I want to work on this function here. Hit the triangle. Now we can get rid of this because we are going to do this right now. So with this triangle function, there are going to be a bunch of early tests, and it's going to be a bunch of early tests, and I just want to do this first of all. Set up a valid render state so that I can just return this at any point, and that will return as if the ray didn't hit anything. But let's start working on this geometrically. So I would strongly recommend pausing this video at any point if you want to work ahead a little bit. But here's what I want to do. The first task I want to do is get the edge vectors from, you know, A to B and A to C, and also get the normal vector. So have a go at that. Okay, and now I'll just catch up. So I'll call this edge AB. That will be a vec3. Get the triangles. Yeah, corner B minus corner A. Okay, excellent. Now I'll just go ahead and do the same thing to get the direction vector AC. Nice and straightforward. And now I'm going to make the normal vector. I'll call that N. Now, it doesn't matter which order we take this cross product, because remember, I'm going with a two-sided triangle. So what I'm going to do is I'm going to take the dot product between the ray's direction and the triangle's normal. Now, question, do I want this to be a positive or negative number? Remember that the dot product will be negative if the vectors are more than 180 degrees. Oh, sorry, more than 90 degrees separation. Does that make sense? If they're facing in opposite ways. So if I'm looking forward and the normal vector that I'm looking at is looking backwards towards me, the dot product will be negative. Now the problem is if the dot product is positive, that means that the light ray and the surface normal are going in the same direction. And that means I'm looking at the back of a triangle. So let's get that, that dot product. Okay, now note that I'm declaring this as a variable because I will be modifying it. So then, okay, if the ray and the normal are going the same way, that's bad. We need to reverse everything. So we'll go if ray.triangle is bigger than 0, I'll just reverse everything. So I'll reverse the dot product. And I'll reverse the normal as well. Okay, so now we'll get to an early exit condition. If the ray is looking sort of side on, so the ray direction is parallel with the tangent direction in the triangle, well then that's really bad. We want to be looking facing the triangle, not looking along the triangle's face, if you know what I mean. Just hold your hand in front of your eyes, and that's what I'm visualizing here. So this will happen if this dot product is 0 or close enough to 0. Now I've reversed everything around, so this should be a negative number. And so what I'll do is my condition will be if that dot product is bigger than a really small negative number. Okay, so this is bad. So what we want to do now is just early exit. So we'll return our render state. And that's it, we've handled the early exit. Okay, so if we get to this point, then we can start solving for U, V, and T. So I'll set up my system matrix that I'll be using for Cramer's rule. So this will be a 3x3 matrix, 3x3. And I'll use a constructor here where, remember before I was talking about the matrix in terms of columns? Well, in WebGPU, matrices are column major order. So I'll just pass in the 3 column vectors. That's the ray direction. And then actually, I just realized, just looking at my notes here, let's go minus. So just go back to the theoretical portion of the video and just verify that this is correct. I'm just doing, instead of A, so I'm doing A minus B, but that's the negative of B minus A. Anyway, so then we'll have the denominator for Cramer's rule, and that is simply the determinant of that system matrix. Okay, excellent. We've got that. Now, another test probably is if the, whoops, yeah, if the absolute value is too small, then we probably won't be able to solve for anything. So just return render state. Okay, now, this is a little weird, but I'm going to reuse that system matrix variable because I've already used this to get the determinant, so that's fine. So remember, I'm solving for U, which is the second component. So I'll just pop in here. We'll have the right-hand side of that equation, which is corner A minus the ray's origin. And now we can calculate U. So we'll have U, which is a float 32. So again, we'll take determinant of the system matrix, divide it by the denominator. Okay, so remember, we've got some tests. To start with, we need U to be bigger than or equal to 0 and less than or equal to 1. So the tests here are if U is negative or bigger than 1, return the render state. Okay. So now what I want to do is calculate V. So again, it'll take a second. I've got some example code up here. What do you reckon we'd have to do to calculate V? Okay, so I'm gonna do that now. So what I'll do is just the same as before. I'll build the Cramer's rule matrix, and V is the third component, so I'll take that right-hand side expression, put it in here for the third component, and then I can calculate V. Yeah, okay. So now, what tests do you reckon we could use for V? Well, we definitely know that v shouldn't be negative. And furthermore, we have that u plus v plus w has to be less than, or has to equal 1. So if u plus v exceeds 1, that's bad. All right, cool. So just return in that case. But yeah, if we get to this point, then we're probably fine. So we can go ahead and solve for t. So now we'll do the same stuff. So I'll go back, take the system matrix, and t is the first component of my system. So I'll just insert that right-hand side vector as the first column vector there. Then it's the same calculation. Okay. And now it's actually very similar to the sphere case because this is, we got t, that's fine. Oh, by the way, we should always be returning the render state. Okay. Let me just go back to the sphere. This code's getting pretty big. Okay. All right. So the question is, we've got the t parameter. Is it acceptable for this range? Okay. So if it is, then we get the position. Okay, no worries. We get the normal, and we don't need to do this. We're not dealing with a sphere. We've already calculated the normal, it's n. We, of course, get the color of the triangle. And yeah, okay. So fingers crossed. Let's see how this goes. Let's just go. Ooh, okay, let's find out. Let's just go inspect. Okay, redeclaration, no worries. It happens, so that was on line 266. Of course, okay, no worries. So we'll just, as I was doing before with the other ones, I just must have forgotten. That's all right. Let's give it another go. Okay. Okay. There we have it. So as you can see, we have a whole bunch of randomized triangles. Now, I will admit this does look a little janky and it doesn't always seem to be reflecting the sky properly, but at least we got something. At least we got it. I am actually happy with that for now. Yeah. Okay, so there we have it. As you can see, performance is going just fine. So what we'll be doing in the next video is, well, previous to this, we loaded a model. We know that models are made of triangles. Now we're ray tracing triangles. So the next stage is we will load a model and ray trace it. I hope to see you there for that one. That'll be a lot of fun. And as always, have a great one, and I'll see you next time. Bye.